Everyone, please welcome to the stage the American Physical Society's Chief Executive Officer, Jonathan Bagger.
Good morning, and welcome to the Kavli Foundation Keynote Plenary Session, entitled New Challenges and Big Questions for the Next Decade. So I'm Jonathan Bagger, CEO of the American Physical Society, and it is a pleasure to be with you at this session here this morning. Before I launch into a couple remarks, I just wanted to let you know that the sessions that have been streamed have been recorded and will be available on the conference platform in a couple of days. But I'd like to give a special shout out to the staff who really scrambled to put the session up. Yesterday's session, where the DESI collaboration announced their first year results, which were really quite surprising, and as some of you might have seen, were on the front page of the New York Times yesterday. So those are that session is available on the platform if you missed it and you would like to see the announcement. Anyway, as you surely know by now, 2024 marks the 125th anniversary of APS. And during the 125 years, there has been tremendous growth in the breadth and scope of physics. And in fact, APS meetings have reflected that growth. We started with 36 at the first spring meeting in New York. Last month, over 12,000 came to the March meeting in Minneapolis, in person, virtually, and in satellite sessions around the globe. And since 1899, the APS mission has really expanded, and it's expanded into something that I hope that we can all truly embrace. Please roll the film. And again, a big thanks to the APS team that produced that video. So like APS, the mission of the Kavli Foundation is to advance science for the benefit of humanity. Established in the year 2000 by the Norwegian-American entrepreneur and champion of science, Fred Kavli, the foundation focuses on stimulating basic research in astrophysics, nanoscience, and neuroscience, and we are grateful for their support. This year's keynote delves into the future hopes and challenges in nuclear, particle, and accelerator physics. Our speakers will also dive into the nuclear science community's recently adopted long-range plan, explore recommendations from the particle physics prioritization panel, and offer insights into the ambitious plans for accelerator-based programs. Introducing our speakers and moderating this session will be the chair of the April Meeting Program Committee, Andrei A. And Young-Ki Kim, 2024 APS President, will close the session. And now, I'd like to turn the floor over to Andrei, who will introduce our speakers. Andrei, thank you.
All right, so thank you, John. I will be very brief because we have three very exciting talks. Our first speaker is Gail Dodge from Old Dominion. Gail is the chair of NSAC, and she was also the boss and leader of this nuclear physics long-range plan, and she will tell us absolutely all about that. So welcome, Gail.
Thank you. Okay, so thank you so much. I'm really honored to be here to present the work of many people, more than 1,000 people who actively participated in developing the nuclear science long-range plan. We're really excited to share the results of that process with you. And I'd also like to thank the organizers of this session and the staff and the Kavli Foundation for making this session possible. Okay, so first I just want to give a bit of a history. The nuclear science community has been doing these long-range plans for a long time. Since 1979, we've had a process of doing these successful plans. These plans have been, I think, well thought out, and in fact, many of the recommendations, almost all of them, have been enacted in the long run. And so we have, I think, a reputation for doing sort of thoughtful thoughtful plans where we prioritize the science. Nuclear science is an extraordinarily broad field, and so it's very difficult, in fact, to do that kind of prioritization, but that is what we have done. And we've done a new long-range plan every 5 to 8 years. The process starts with a charge from DOE and NSF to NSAC, the Nuclear Science Advisory Committee, and NSAC forms a writing committee, and the Division of Nuclear Physics in the American Physical Society are the ones that organize a lot of town meetings and organize the early input into the process. So just a little bit about that. The DNP organized 3 town meetings as part of this process. There was one on hot and cold QCD at MIT. Then we had nuclear structure, reactions, and astrophysics at Argonne. And finally, fundamental symmetries, neutrons, and neutrinos at the University of North Carolina. The charge we received came in July of 2022, and the plan was completed and adopted in October. So it was a 15-month process, which in fact was a little bit too compressed, if I do say so. But that's a sort of the timeline we were working with. Okay, so as part of this process, the committee received a lot of white papers, I think 24 white papers. They're archived on the nuclearsciencefuture.org website, and these documents are an incredibly valuable resource for the community going forward as well. And they're at this website, so people can look at them and go back to them, but it's a really excellent summary of the many accomplishments in the field and the opportunities for the future. Okay, so here's the writing committee, which we call it the writing committee. It consisted of 62 people, including 2 international observers, and we formed 11 subcommittees to do the bulk of the writing in the organization and working on the budget. So what I want to do is present to you the recommendations, but also with a lot of comments interspersed. And as we have historically done, the community distills all of this input into 4 recommendations. That's what we've done in this case as well. And I want to, because I'm going to probably forget later, I want to invite you to really take a look at the cover art next time you have a chance. If you look, you will see a lot of different things in there. And I want to say that Philip Gray at Oak Ridge was just outstanding in developing that cover art. We're so happy with it. Okay, so I'm going to go through the recommendations one by one. As you can imagine, the wording was very carefully crafted. Recommendation 1 really addresses the importance of taking advantage of the opportunities and the funding and this is the investment that has already been made in the field. Very substantial investment has been made, and we emphasize that in order to take advantage of those opportunities and realize the scientific discovery potential of the investments that have already been made, requires everyone. We have to draw on the talents of everyone in the nation to achieve that goal. So how are we going to do that? How do we recommend that we take advantage of the investments that have been made in the past? Well, we identified 4 pillars. I mean, the whole report is filled with the opportunities and the accomplishments. But these 4 pillars I want to go through because I think they're extraordinarily important and they are at the heart of our recommendations. So I'm going to go through them one by one. The first thing we need to do to implement that highest priority, which is to capitalize on previous investments, is to increase the research budget. And here what we did is we acknowledged and emphasized that people are at the heart of the science that we do. It's the postdocs, the undergraduates, the graduate students, right? The faculty, staff at national labs. It's a whole ecosystem of people, and those people are funded by the research budget. And that budget also funds, for example, smaller labs, they're not small, at universities that are accelerator-based. It funds, equipment upgrades and that kind of thing. This budget is absolutely crucial to the functioning of the scientific community, and this budget has been declining a bit as a function of total expenditures in nuclear science. So we see that as quite a concerning situation and argued strongly for the importance of a healthy research budget in order to capitalize on the work that's already been done. We also emphasized, as part of this bullet throughout the report, the very important interplay between theory and experiment. So it is important to emphasize how critical to science is that healthy exchange and interplay. And so we tried to really elevate the importance of the theory throughout our document. Next, we emphasized the very critical and important the importance of effective operations of the user facilities. Obviously, the user facilities are at the heart of most of the data that we take, not all of it. And a robust and optimized running schedule, operational schedule for these facilities is extremely important for the field as well. And here I think it's particularly important to point out that we have, for example, EFRIB, which is almost brand new and has an extremely exciting program ahead of it. We have the program at RIC, which is completing its mission in the next year or two. I'm not sure exactly on the latest timing of that, but that program of measurements that is planned to be completed at RIC is extraordinarily important. And we wanted to highlight the importance of adequate funding for the operations of the facilities. Then, very importantly, we highlighted the problem of compensation for graduate students and the fact that their compensation is often not commensurate with the cost of living. This is, I would argue, an extremely big challenge for our field, not just the field of nuclear science, probably the field of physics or maybe science in general, because the whole scientific enterprise, for the most part, is very critically relying on graduate students. And we really spent quite some time, which I want to go into, identifying the nature of that problem, the size of that problem. We contacted universities, we got response from some of them, and what we did is we compared what they said they paid their graduate students and annualized it to the cost of living locally using the MIT cost of living calculator. And we found that only one university that responded to us paid the cost of living adequately, and the rest of them were, there was a deficit. That average deficit was $5,500 per graduate student, and this is a very, very real concern. Because what we have learned, we did several things. We did a survey of faculty at universities, but we also did a survey of graduate students. And we found that 65% of them struggle to meet basic costs. We also found that often students cited the fact that they were able to accommodate an unexpected expense was because of family support. So if people don't have that family support, they're less able to persist in science, right? And this just can't continue. We don't want to filter out anyone who doesn't have family support from participating as a graduate student in our science. So we really emphasize this and the importance of correcting the gap that has emerged between what graduate students are paid and the cost of living locally. So we really emphasize that point. Now, I wanted to say one other thing, and that was that Evie Downey gave a whole talk about this issue previously. I think that talk is recorded, and I would really recommend that you look at it. We also published or posted the survey of the graduate students. There was a lot of interesting information in there, and I think it's useful to take a look at that. Okay, so finally we said that it's very important for us to expand our policy and resources to ensure basically a welcoming environment that is one that all people can enjoy the climate in nuclear science. So we really emphasize the importance of creating of workforce, let's say, proposals that can help us ensure a welcoming climate. I'll say more about that in a little bit. So then I want to go on to recommendations 2 and 3, which are of equal priority. And these cover the electron-ion collider, which will elucidate the origin of visible matter in the universe. This is going to be at Brookhaven National Lab. This project is underway. As a very high priority, we must complete that project. And then neutrinoless double beta decay experiments, another extremely compelling and important program that we must undertake to understand, and I'll say a bit more about that in a second. So I'm going to start with recommendation 2. We listed them in the same order as the 2015 plan. Recommendation 2 was that we recommended as very high, as our highest priority for new experiment construction to undertake a campaign of neutrinoless double beta decay experiments at the ton scale. And I want to say a little bit more about that. As you notice, if you look at the cover art, you have, for example, neutrinoless double beta decay represented there. So why is neutrinoless double beta decay so important and so compelling? So in regular beta decay, neutron decays to a proton and emits an electron and an antineutrino. Double beta decay is, of course, twice that, 2 neutrons releasing 2 antineutrinos. But neutrinoless, and of course, double beta decay has been observed in 14 isotopes. Neutrinoless double beta decay has not been observed. That would be where that process takes place with no production of neutrinos. So in other words, the neutrino was its own antiparticle, and those 2 neutrinos annihilated each other, right? So an observation of neutrino-less double beta decay would be absolutely groundbreaking. Because for one thing, it would mean that the neutrino is its own antiparticle. That in itself is an enormous discovery. It would mean that lepton number is conserved. In other words, you can create electrons without creating an associated anti-lepton with that. And it can help explain why we have more matter than antimatter in the universe. Obviously, one of the fundamental questions of our time. The nature of the neutrino, and why do we have this asymmetry between matter and antimatter in the universe. Also, the rate of observation of neutrinoless double beta decay would have implications for the masses themselves of the neutrinos, another extraordinarily important issue. So the discovery potential is huge. The community found this to be a very compelling opportunity. So let me move on to the status of the neutrinoless double beta decay experiments. There are 3 experiments that are ready to go. There's been a lot of extensive R&D since the last long-range plan, and different isotopes are used in each of these different experiments. And it's extremely important that different isotopes and different detector technologies are used as part of this campaign, because that will help you understand backgrounds and interpretation of the signal. So those 3 experiments, Legend, Nexo, and Cupid, have undergone millions of reviews and are essentially ready to begin. Let me turn now to the electron-ion collider. We recommend the expeditious completion of the EIC as the highest priority for facility construction. And the yellow box shows you where the EIC is located on our cover art. So for the electron-ion collider, I want to point your attention first to these 3 artistic renderings on the right. These come from a collaboration between MIT, Jefferson Lab, and Center for Art and Science. And so what you see is 3 different values, let's say, of the momentum fraction for the partons inside the proton, or inside the neutron, inside the nucleon. So when you are looking at high X or high momentum fraction, what you're seeing is the valence quarks, the 3 regular quarks that we think of as making up the proton, up, up, down, or as you see here, red, green, and blue for the color, to create a color neutral object. So when much of the work that we've done so far has been to identify the momentum and longitudinal and transverse distribution of those quarks, for example, at high X. That's the kind of work that we've been doing that's been extremely fascinating at Jefferson Lab. But if we want to understand low X, which is represented by these other plots, there you're starting to go to lower and lower momentum. And what you see there are the C quarks and the gluons. So the C quarks are the quark-anti-quark pairs that are created and destroyed in the energy of the nucleon. And we really don't have a very adequate understanding of those C quarks. And the gluons also, which of course are interacting, are the carry the strong force and interact between the quarks. Those gluons, not only can a gluon split into 2 quarks and recombine, but as you go to lower and lower momentum fraction, what you see inside the proton is just a seething mass of quarks and gluons, right? We don't understand that. And not only do we not understand that, but it's critical to understand that in order to understand things like the mass and the spin of the proton. We don't understand those things at a fundamental level. And that's what the electron-ion collider allows us to do. It allows us to go down in X to get at those extraordinarily important low X components, those partonic components inside the proton. So the electron-ion collider would collide polarized electrons with polarized protons, polarized light ions, and heavy ions. And as I said, it allows us to study the C quarks and the gluons. This will help us elucidate the mass and the spin of the proton, the spatial and momentum distribution of these low X partons, the concept of gluon saturation. As you go to lower and lower momentum, the gluons are splitting into lower and lower momentum gluons, and the density of those gluons in that fixed volume of the proton is getting higher and higher. Does that saturate? If it does saturate, what does that mean? And then, of course, modifications of parton structure when you go into the nucleus, and also the formation of hadrons. For example, if a quark is ejected, how does that become a hadron? Because we know that we can't observe quarks in isolation. So the discovery potential here is enormous. And the community adopted and reaffirmed the importance of the electron-ion collider as an absolutely compelling opportunity that must be pursued in the coming decade. And so the status of the electron-ion collider is that it's essentially underway. It's a partnership between Brookhaven and Jefferson Lab. There's an EPIC detector, which will be at the 6 o'clock location. And it's an extraordinarily large user community with 1,400 people from all over the world. Accelerator physics is going to be an extremely important part of designing and building the electron-ion collider. And we'll hear more about accelerator physics at the end of this session. CD2 is expected in 2025, so this project is well underway. Let me go on to recommendation 4, which recommends capitalizing on the ways that other unique opportunities that will come along can advance discovery science and applications for society. And let me give you a few examples of what we mean by that. We identified examples such as EDM experiments or neutrino mass measurements or LHC upgrades. There are a bunch of upgrades that are planned or desired that will make a tremendous difference in the potential that we have of taking advantage of what we have already invested. And those strategic opportunities are important, and they're laid out, in the plan. We also highlighted the importance of detector and accelerator R&D. Again, I won't say too much about that, but also the importance to our field of these emerging technologies, computation, quantum information science, and technology. And of course, artificial intelligence and machine learning. These different computational areas are not only contributing to our science and enabling the science, but also our scientists in the field are, we believe, pushing those fields forward as well. So it's a very, very synergistic opportunity there. So let me move on quickly. There are many benefits of this work to the nation. We have articulated those in the report. In addition to the fact that our work is it touches and interacts with and is synergistic with many other types of science. We also have the fact, and the very important fact, that we produce trained students, a trained workforce that affects many areas of society. So for example, students that are trained to go into fields like nuclear non-proliferation and security, or isotope production for medical and other needs. There's also so many applications that come from nuclear physics, for example, in energy, in healthcare, in homeland security. These things are articulated in the report, and I think it's important to understand that, again, as I said already, the development of computational techniques is a really important outgrowth of the work that we do in nuclear science. So I want to emphasize to students that nuclear science is an area, if you're interested in science and you want to work on science and you want to make a difference, nuclear science is an outstanding area to go into, because so much of what we do does have very, very positive applications for society. So more about workforce. As you know, as I've already said, we really emphasize the workforce part of our proposal. We thought about ways that we are doing a good job of creating a more inclusive environment and getting more people into the field. And some of those, for example, include the conference experience for undergraduates. That's where undergraduates come and give posters and participate very fully in the fall meeting that we have, the Division of Nuclear Physics fall meeting. We have the DNP Allies program. We have gender minorities in science social. This is just 3 things that I'm listing, but what I'm trying to get at is that the community has worked very hard for a long time now to be doing whatever we can to get more people in the field and to make sure they're feeling welcome and participating. But there's so much more that we can do. And one of those things is to continue and to expand opportunities for undergraduate research. That is so foundational and so critical. I think we all know that. Compensating graduate students at a level commensurate with the cost of living. I already mentioned that, extremely important. But we can establish policies from the funding agency, for example, that make it clear about medical and family leave, and perhaps set the standards for those kinds of issues. We can do more to support appropriate skill development at conferences. I mean, we already do quite a bit of that, but I think there's a lot more that is foreseen. And importantly, to provide guidance and resources to establish community agreements, not just at conferences where we have code of conduct, but also at national labs and in collaborations. So that, and of course, not just community agreements, but enforceable community agreements. It's a complicated area, and we're hoping that the funding agencies, or perhaps the American Physical Society, can provide some guidance and some help to the community in that area. So let me quickly summarize. The nuclear science community has come together. We had a long process, but we came together to identify look at all the progress that's been made and all the opportunities in the future, and to identify priorities. Those priorities were hard to do. That took a lot of work, and we had to fit those priorities within certain budget scenarios. We identified very compelling and clear priorities to proceed with the electron-ion collider and to initiate a campaign in neutrinoless double beta decay. We pointed out, I think it's obvious, that to maintain our world-leading position in nuclear science requires investment in people, in facilities, and in projects. And we emphasized the importance of creating a welcoming and respectful environment to allow all to participate in the scientific enterprise. So we concluded that we are on the threshold of a new era of discovery, and that the future is very, very bright. And I want to thank many people. The writing committee was fantastic. The APS Division of Nuclear Physics was extraordinarily important in this whole process. The NSF and DOE leadership were very, very helpful, and the Oak Ridge communications team were tremendously valuable as well. So nuclearsciencefuture.org is the website where the white papers are listed, and so with that, I will take any questions.
All right, thank you for the really nice talk. As you've grown accustomed to, if you have any questions, please walk up to the mics that are in the aisles. and we'll give people a couple of minutes to get there, but we can start over here.
Thank you, Gail. So the issues that you touched on about the environment and supporting undergrads are obviously not just nuclear physics issues. So maybe could you speak a little bit about how we might work with our colleagues in other divisions and what the APS might be able to do?
Yeah, I think that's extremely important. I think we probably need to have opportunities to tell some of our colleagues in other areas what we do and hear what they do. I'm sure they have many things that they're doing as well that would be very valuable for us to copy and learn from. And I think the American Physical Society can certainly provide some leadership and guidance to help make that happen. But I would hope that we would learn from others about what they're doing. I don't know if that's what you were getting at, but yeah, I completely agree that a real effort is needed in that area. So.
I can add very briefly that the APS is heavily involved in working towards getting better support for graduate students, especially to reach this living wage threshold, which seems to be a no-brainer, and it is a big thing for the APS as well.
Not only is it a no-brainer, but, and I should have mentioned this when I showed that plot, but we estimate that it would take about $8 million to correct, in the research budget, to correct that, at least for nuclear science. And as you said, APS is already doing a lot, and they're going to help, I think, with some of these community agreement issues. So, yeah.
So what is APS doing as a collective community to incorporate high school students into like nuclear programs?
That's an excellent question, which I don't think I know the answer to. I think they make it possible for high school, I mean, maybe someone else should answer that who knows that, the answer to that question, but are you a high school student?
Yes.
Yeah, so did they help you come to this meeting, or was that?
FRIB did, but not.
FRIB did, I see, yeah. Okay. I think one thing I've seen, this may not completely answer your question, one thing I've seen is that APS has done a great job now of labeling the different parts of the program for what's appropriate for undergraduates. I think it makes it a lot easier to come into the conference and see what sessions you may want to attend. You can tell me if you would disagree with that, but I think that's extremely helpful to make it comfortable for people who are not professional scientists to enjoy the conference experience.
Got it. That makes sense. Thank you.
Yeah.
And I think nuclear physics funding also goes to funding research experiences for high school students in specific locations as well. I think maybe at the INT, I don't know about the FRIB Alliance, but yes.
Certainly the conference experience for undergraduates is something which, if it's not being done in other communities, would be worth copying. I don't know, Shelley Lesher's probably here. We've been doing that for more than 20 years. And that's where students come and give a poster, and they have a whole program of activities. I think we have statistics in our report that show the long-lasting benefits of that and how many of those people persist in nuclear science or in science more broadly. It's extraordinarily effective. And so the conference experience for undergraduates is one thing I would recommend to any unit that's not doing that already.
Do we have any more questions or comments? Here's one more.
Yes, hi. I had a question about how do we change the perception that it's impossible to make the jump from academia to making contributions to actual nuclear policy in the US government? Because I think that's the way that a lot of people feel. And I feel that we have something to contribute, but we just don't know how to make that jump.
That's an excellent question, because I'm much better prepared to say that many people who get trained in nuclear physics go on into industry. I mean, industry snaps up people in nuclear science because they have all these computational skills and of course. But to go into government, I know there are some programs, of course, that allow people to go and do fellowships. I don't know how many spots there are or much about that. So I think that's, I think if people care about societal change, that's an excellent avenue. And maybe there are other avenues as well. So I'm going to have to think about that. I don't know. Maybe someone else does know. Do you know? Yeah. How to make that leap. One thing we'd like to do is to have, to document more career pathways. And so maybe documenting on our website how some people have made that leap would be a first step. So I appreciate that suggestion.
Thank you.
Thank you. So there's
Hello.
one. Yeah.
Thank you very much for a comprehensive summary. With regard to the graduate students' compensation, what do you think are the hurdles? I don't think it is the funding agencies, but where can we make progress? How can we accomplish higher compensation?
Well, there are many hurdles, and some of them are in the funding agencies. The funding agencies acknowledge this and everyone agrees, I think, that this is an important thing to do. But I think as a start, we have to ask in our proposals for the amount of money that's a living wage. And I'm not sure that we're doing that, because I think we all have, our research budgets are so constrained, and we don't have enough money anyway, and we're afraid if we pay our students more, we won't be able to have as many students, for example, right? And what we articulated, I think, very clearly is that we must pay the students the cost of living, and we cannot contract the workforce in doing it. And I think that the agencies are incredibly, receptive to that. So I would just recommend that everyone put that in their grant proposals as a starting point. There's other hurdles like, unionized schools, but let's put it this way. If we start asking for it and we start getting those kinds of salaries, it's a marketplace, and some universities will do it and others will have to follow. So we just have to start.
Yeah, I mean, I was
Yeah.
wondering whether universities are themselves a hurdle.
In the case, well, in the sense that some universities want everyone to be paid the same.
Yeah.
At my university, they just raised the graduate wage, but they raised everyone to the same number. So the people in physics who are already being paid a lot have almost no increase, but people in English got a huge increase, So universities can be hurdles as well.
So we'll take one last question.
Yeah, so not a question, a comment. I'm Shane Larson from Northwestern. I'm also the chair of the Prairie section, and I just wanted to comment about the policy. So all of the professional societies, including APS, have mechanisms for you to become engaged in policy. At the section level, we visit the Hill every year, and APS and their staff provide excellent training and advice about how to engage in that landscape, and they will facilitate your opportunity to talk to your representatives in the areas where you are. Those of you who are early in your careers, all the societies, including APS, have fellowships, policy fellowships. So if you want to get into policy, you can take a policy fellowship instead of going to a postdoc or industry or something like that. So those opportunities do exist, and the society is one way to do it. So, okay.
Oh, and that reminded me that I intended to say how important it is to participate in these advocacy days on the Hill, right? So the next one is April 16th. I haven't done too many of them. I did one as part of the long-range plan, and I was amazed how useful it is. I would recommend that everyone do that. And it's great to bring your students with you. Students should go. It's so interesting to have that experience, to go and sit there and talk to those staffers and explain the importance of the science. They love to hear from students. And so I would strongly recommend April 16th is the next one of these. Do it if you can. It's an extremely empowering experience. And it also gives you some hope and some feeling like, these congressional staffers, they genuinely care. And those are the people that we need to be talking with and explaining. So, okay.
So
Sorry,
there's somebody running to the mic, so we'll let her ask a question.
So one of the issues we have whenever we're arranging these visits is that we don't have money to support sending people.
Yeah.
And especially students. Like I asked my department head and he's basically said, nope, you guys are on your own.
Yeah.
And we're seeing the impact of not being able to send people.
Right.
So what can we do, and maybe can the APS help us with that?
Or the Kavli Foundation, I'm thinking, could help us with that. Yeah, no, that's an extremely important point, because you can't use your grant dollars to send people to Washington to lobby for funding for, for nuclear science. So I think there are basically philanthropic donors at most universities who are interested in supporting that kind of experience for students. So that might be one way to start. And maybe the department can use some of their funds to help support that. So.
All right, so thank you, Gail. Okay, so the next speaker is Professor Hitoshi Muryama from Berkeley. So Hitoshi took the impossible mission of leading what's called a P5. He will let you know what that means. And that's the equivalent of the aspirations and challenges for particle physics for the next decade and beyond. So, Hitoshi.
Okay, is the microphone on? I suppose it is. And let's see if the slides get started. So as Andrei introduced me, I chaired the Particle Physics Project Prioritization Panel, P5 for short. And our report came out just last December, so I'd like to base my talk on that. But I'm afraid I actually made this talk a little bit too colloquial, because knowing that there are many students, so for the professionals in the audience, I apologize ahead of time that I'm going to insult your intelligence, so sorry about that. But anyway, so we came up with a report back in December titled Exploring the Quantum Universe, Pathways to Innovation and Discovery in Particle Physics. So the process is actually very similar to the nuclear science process with some differences. So we always start with a community that's the same. So in our case, the APS plays a major role in organizing what is called the community study. And we call this community study snowmass process simply because the community used to meet in snowmass. But snowmass has become such an expensive summer resort of some kind. There are field physicists can't afford to go there anymore. So we actually changed the location these days to places like Minneapolis and Seattle. But nonetheless, we still call this process snowmass. And it is organized by the American Physical Society, especially divisions of particle and fields. So Yang Ki actually started it, and then handed over to Tao Han and Andrei. So he actually went over the 3 leadership of DPF. So it took a long time, partly because of the pandemic. And after 2 years of this process, the funding agencies came up with a charge and the budget scenario we should actually deal with. And then I was told to form this committee called the Particle Physics Project Prioritization Panel, P5. And the one difference from nuclear science is that in the case of nuclear science, Gail, who is the chair of the Nuclear Science Advisory Committee, doubles up as a leader of this process. And in our field, the chair of the Hydrogen Physics Advisory Panel, HPAP, actually appoints me and let me run the process, and she remains an ex officio member of the process. That's one major difference, but pretty much the idea is the same. We always start with the community, try to understand what community wants to do, what is important science, and so on and so forth. Then we try to coalesce it within the budget scenarios given from the funding agencies. And the report, of course, goes back to funding agencies, in our case, the Department of Energy, High Energy Physics Office, as well as the Physics Division of National Science Foundation. But we very much hope that this kind of report will be read, not by just the agencies, but also people in the White House, Office of Management and Budget, Office of Science and Technology Policy, and also congressional staffers and even policymakers, so that what we recommend can be implemented and funded and supported. So anyway, that's the idea of the process. And here's just an excerpt from the chart. It shows 2 budget scenarios. One of them shows only 2% increase per year, which is very bad scenario because we assume 3% inflation every year. So this actually means 1% erosion every year. Another one is more reasonable, together with a hike according to the CHIPS and Science Act that was already authorized, and followed by 3% increase every year after that. So these are the 2 budget scenarios we had to deal with. And within these 2 budget scenarios, we have to evaluate project costs and come up with a plan for the next 10 years within the 20-year context. And just to show you how the budget might look like, and so this is a very rough estimate. So we were given the budget profile, and we took just the 30% of that to be able to be spent on new projects. And ongoing projects already saturates the budget for the next 5 years. And even if we exclude some of the largest proposals made from the community, even the rest still overshoots the budget profile quite badly. So that immediately means that we, as a panel, have to chew with all the proposals and come up with really tough decisions, what we should recommend, what we should not. And this has certainly not been an easy process. And we were told from the Dr. Harriet Kahn, who is now the interim director of the entire Office of Science. So she came to SNOMAS and talked to us. What are the key elements of successful P5? And we were told that we should be well informed by the science community, which we know how to do. We listen to the SNOMAS process. We need to set a grand long-range vision for the US particle physics, which we'd love to do. But we need to face budget constraints realistically, and we have to say we community made tough choices, so we have to say no to many things. And in addition, we need to come up with a balanced portfolio between domestic and international, and also among small, mid-scale, and large projects, which is very important, especially to nurture the early career scientists, to give opportunities to do a small-scale experiments. And in the end, community engagement is critical to success because bickering scientists get nothing. So we need to have a broad agreement among the community. And you already see this is a contradicting requirements. So she tells us we need to say no to many things, but still we need to keep everybody happy, and that looks impossible. So that's the impossible task that Andrei was referring to. So my first task was to form the panel to actually grapple with all these questions. We have 5 international partners, and we have people from all different areas of particle physics. But I really appreciate their service because each one of them have their own scientific interest, but they managed to set their own interests aside and try to think for the sake of the good of the whole community. And so we work very collegially. We never voted on the panel. We talked through every single issues together and eventually came to a consensus. So I really appreciated every single panel member on P5. And it was a long process from the beginning of the snowmass. It took almost 4 years towards at the end of the process. We had many town meetings for the information gathering phase. We had closed meetings for the deliberation phase. We had separate meetings for many different partners. And so that was a long process, and it was very intense. And at the end of the day, we came up with very difficult choices, what we should recommend and what we should not. What is shown in this table, that's what is shown in solid black, are the projects, unfortunately, we could not recommend. And so we really had to make tough choices. So we had to say no to quite a few things. So when I mentioned this role to my daughter, who actually went to an art school, she volunteered to actually draw a picture of me being the most hated man in the community, getting all the pies and shoes and tomatoes. And in addition, I actually pasted troublemaker to my name tag as well for this reason. So one thing we had to do is to actually grapple with the question, who are we? What is the science we would like to do? What is the definition of the particle physics in the United States? And of course, the word particle physics is traditionally associated with this idea that we're looking into smaller and smaller constituents of matter around us. So starting from the normal bulk material to molecules and atoms and nuclei, protons and neutrons and quarks, and going for the smaller and smaller objects has been a hallmark of particle physics. And that is still true. So we call this kind of science team decipher the quantum realm, looking for the quantum material that we are made of. But for some reason, the US particle physics community has been also interested in looking for things that are becoming bigger and bigger, namely the whole universe. And the universe is actually driven by entities we don't get to see in telescopes, such as dark matter, dark energy. It started with inflation and so on and so forth. So trying to understand what's hidden in the universe is the other science team we call Illuminate the Hidden Universe. And both looking at the quantum realm, we have the standard model particle physics. Also looking at the hidden universe, we have a model called lambda CDM's model of cosmology. And we know both of these standard models are incomplete. We are still missing something in a big way, trying to piece things together to come up with a comprehensive understanding from the smallest object to the largest, namely the universe. So we have to discover many things in between, and that's a science team we call Explore New Paradigms in Physics. And the way we came up with the title of the report is to pick one word from each science team, hence explore the quantum universe. And so that's the title of the report. And under each of the science teams, we have 2 science drivers. And that looks actually similar to the science drivers from the previous P5, looking at neutrinos and Higgs boson, dark matter, and what drives the cosmic evolution, and looking for new particles and new quantum imprints of new phenomena. But these wordings actually reflect something we have learned over the last 10 years. So the wording has been changed slightly. For example, the previous P5 said, identify dark matter, because back then we thought we knew what dark matter was. It has to be WIMPs, weakly interacting massive particles, maybe axion. So we had to identify them. But over the last 10 years, we learned that the possibilities of dark matter is actually vast, ranging over 90 orders of magnitude in their masses. So we have to actually ask the question in a different way, determine the nature of dark matter. So each one of them, of the science drivers, had been rewarded, reflecting this kind of evolution in our thinking the last 10 years. But this kind of graphics is too complicated for a logo or branding, so we drastically simplified it from this rich graphics to this simple logo with 2 triangles. So the triangle on the left in magenta represents going forth to smaller and smaller. The one on the right in cyan represents looking at things becoming bigger and bigger, and they intersect. And these 2 science teams are inseparable, and that defines a single field of US particle physics, and that's the way we defined it. And similar to the nuclear science report, the first recommendation is really putting an emphasis on ongoing projects. And we had to review each one of them very critically and to see if they're really worthwhile doing at this point. And at the end of the day, we came out with the answer resounding yes. We should actually keep doing what we have been doing. And high-Lumi LHC is going to increase the data set by order of magnitude beyond what we have, and it would have the first measurement of the self-interaction among the Higgs boson and extending the reach when you're looking for new particles and new phenomena. And the DEW and PIP2 is looking for the neutrino oscillation by shooting the beam of neutrinos in Illinois to a detector in South Dakota. And the Vera Rubin Observatory is being built as a joint effort between DOE and NSF and in Chile, and that is supposed to give us much better information on what exactly is accelerating the expansion of the universe, namely dark energy. And there, the partnership is actually very important. So what we have learned from various experiments looking at the neutrinos, which is also a joint effort looking at the solar neutrinos by nuclear science community and atmospheric neutrinos by the particle physics community, we know that there are 3 neutrinos at the least, but we don't know which way that their states are ordered. And that's an issue called mass ordering. And a dune would actually determine which ordering is right at a very high significance, better than 5 sigma. And depending on which ordering turns out to be true, the total mass of neutrino would turn out to be different. And this is the quantity that you can measure in the universe today. So we believe that neutrinos have been created in the early universe when it was only 1 second old. And that's the earliest moment, even earlier than the moments we have probed already in understanding of the early universe. And whether what is actually we can observe in the sky today versus what we measure in the laboratory, that cross-check would tell us what the state of the universe was like when it was only 1 second old. At the same time, this also provides yet another important information on the nuclear science effort and neutrons about double beta decay, and what they will learn and what we will learn this way should be also compared in a critical fashion. And for example, the lack of events observed by the double beta decay experiments, while determination of inverted ordering by this Dune experiment, would tell us that neutrinos have to be Dirac neutrinos instead of Majorana neutrinos. So again, the partnership is actually very important in this kind of science. And we also said that all these smaller efforts need to be continued as well, and I don't go through the entire list. And looking into the future, so we recommended 5 major initiatives, and I don't actually read this text, but rather jump into science, what they are about, starting with the neutrinos. And as Gail already hinted on this, the one very interesting thing about neutrinos is the possibility that it might have played a major role in actually saving us from complete annihilation. So what we know is that universe presumably started with the inflation. There was a huge amount of energy, and when energy turns into matter, that creates an equal proportion of matter and antimatter 1 to 1. So that's the way the beginning of the universe looked like. But what we need is some process at some point by somebody to pick 1 out of the billion antimatter and turn that into matter, so that you have a tiny difference between matter and antimatter, which we call asymmetry. And the only candidate matter particle we know of that can possibly do this is actually neutrinos, because every other matter particles we know, like electron, has an electric charge negative that can never turn into its antimatter counterpart that has a charge positive, because electrical charge is conserved. But for neutrinos, neutrino has charge 0, so antineutrino also has charge -0. It's the same thing as 0. So it could have possibly done this. And if they have actually done this conversion of antimatter to matter, pretty much all of them still annihilate away, but there is a remainder, and that is meant to be us. So the idea is that this may be the way we were saved from complete annihilation. So if that's the case, the neutrinos are actually superheroes we owe our existence to. So we don't know if this is true yet, but that's why we would like to understand sort of comprehensive picture on what's going on with the neutrinos, and that's the way we came up with this DUNE program, Deep Underground Neutrino Experiment. So beyond the effort that is going on right now, so we recommended to improve it to actually have a much bigger exposure in data up to 600 megawatt kiloton a year. And our panel had to struggle with how we can actually make that happen within the budget that is given to us. So we scratched the plan of going to doubly a more intense beam, because that would require a new set of accelerators, but small modification of the existing one can actually give us pretty close to it. And then we can actually even not build the fourth detector for now, which is left as a module opportunity for the future to enable more science. So this is the way we try to accommodate this exciting science into our program. Another big excitement in science is what is called the Higgs boson. And the Higgs boson was discovered way back in 2012 by the Large Hadron Collider at CERN in Europe. But we still have a lot to be understood about this Higgs boson, because once again, we owe our existence to it. So for some reason, Higgs bosons was zooming about just like air molecules in this room when the universe was very hot. But as the universe expanded and cooled, at some point, it froze into empty universe. And it's still out there, really frozen in a dense fashion right here where we are. And this frozen Higgs boson actually disturbs the motion of every matter elementary particle we know of, such as electron, and electron gets slowed down. That's why it can happily move around inside the atoms. So here's an atom. And if the Higgs boson in the universe for some reason would evaporate at this instance, then all the electrons inside the atom will start flying apart with the speed of light, and atoms would disappear, and so would our bodies within a nanosecond. So, it's kind of important to understand, why has this particle got frozen in empty space somehow? So our empty space is filled with all superheroes who are actually trying to keep us in one shape. So to understand this property of the Higgs boson better, we'd like to move on to next generation of the collider experiments. Once again, we struggle with the question how we put together within the budget profile given to us. So unfortunately, we have to give up the idea of building a new facility on the US soil, but rather rely on an effort being done elsewhere in the world, like in Europe, in Japan, and to work together on an offshore Higgs factory. And that is going to be a machine based on E plus E minus collision. And that would actually help us a lot about understanding what Higgs boson actually is. Is it an elementary particle or a composite particle like Cooper pairs in a superconductor? Why is this particle frozen in the universe today? Or does it decay and talk to dark sector and dark matter in some way? And all of these things can be studied once these machines are ready. And beyond that, we really would like to answer this question, why has this particle frozen in the universe today, which would require measurement of how Higgs boson would interact with itself, called self-coupling. So we set a goal that we need to do an order of magnitude better than what the hydrogen OHZ can do, which means 5% measurement of Higgs self-coupling. And it turns out that the only way you can do it is by going to even higher energy machine in the future. And one proposal in Europe is to build a 91-kilometer tunnel and put a proton-proton collider in it. Unfortunately, we don't have technology ready to go for this kind of accelerator, because we need to develop a very high field dipole magnet to bend the beam to stay inside this large tunnel. Another possibility that attracted a lot of attention in the US is to build a muon collider instead. And this is also probably an even more challenging goal, because as you all know, muon is a particle that actually decays in 2.2 microseconds. They are not around us. So you need to first make them, collect them, cool them, accelerate them, and collide them, all in a big hurry. And for an interesting fact, of course, is that we know that once the particles accelerated close to the speed of light, times get stretched, time dilation effect, muons live longer. So for 2.2 microseconds, they can't even make 1 kilometer. But once it's accelerated to high energy, it can make many thousands of turns inside this kind of ring. And I'm sure Andrei will talk more about how challenging this kind of idea would be. But if this is possible, then we can fit much higher energy machine, which goes up 10 times higher than current LHC, to a size which is a third of the LHC, and it may fit in on the Fermi Lab site. So that will be a very exciting possibility. So we would like to develop technologies for it. So this kind of R&D would allow Fermi Lab, which as a potential host, to continuously expand the accelerator complex while producing world-class science. So that's an effort we call our muon shot. And there's even third technology people are talking about, which is more futuristic possibly, and based on the Wakefield idea. So what we argued in the report is that we have to invest in the future by doing a vigorous R&D. So to be able to carry our science beyond the program we recommend today, we need to spend significant resources in developing new technologies so that would enable science 10 years and 20 years from now. So that is actually another centerpiece of our recommendations in the report. And that shows up at the top of the recommendation number 4, vigorous R&D towards a cost-effective 10 TeV particle center mass energy collider. In addition, we argued for an investment in targeted areas in a community like theory, computing, instrumentation, and accelerator. So this is actually a part of the recommendation as well. And in addition to Higgs boson and the neutrinos I mentioned already, so there is a very interesting question about how we came to be. So the idea in the community today, which is a part of this lambda CDM model of cosmology, is that universe started out incredibly tiny. The 13.8 billion light year stretch of the universe we see today was much smaller than the size of an atomic nucleus. As a matter of fact, less than 10 to the minus 30th centimeters. So it was a microscopic space and time. So in the microscopic space and time where the quantum mechanics ruled, there was this quantum fluctuation which caused the fluctuations in densities and energies all along during this process. And this tiny universe got stretched to a macroscopic universe by a process called inflation. And once it gets stretched, these tiny quantum fluctuations would become classical and burned into this picture of the Big Bang taken by the cosmic microwave background satellite. So these tiny temperature variations we can observe today when the universe was young actually is believed to come from this quantum fluctuation. And these tiny variation in densities at the level 10 to the minus 5 had been grown by dark matter due to its gravitational pull, and that eventually became stars and galaxies and us. So that's the theory we have today, how we came to be. And we don't understand each step in this picture because we don't know what dark matter is. But based on computer simulations, starting with this initial condition where density fluctuation is only at the level 10 to the minus 5, you see on the left panel the wrong kind of universe without dark matter, and there's basically no structure even 13.8 billion years later, and hence not us. But in the universe, the correct universe with dark matter, their gravitational pull will bring the small density fluctuation to a more excess and stronger gravity, pulls more dark matter in, even more strong gravity, and the structure grows non-linearly that way, and eventually leads to an existence and structure we see in the universe today, including us. So dark matter was responsible of creating a structure in the universe we see today, but we don't know who dark matter is. And there has been this idea that the WIMPs is one of the prime candidates for dark matter. And we are coming to the point where we can actually really try to finish up this job looking for WIMP dark matter because we have the sensitivity of the detector actually developed to the stage that even the neutrinos, which have been so difficult to observe, eventually becomes the background when we look for dark matter. And that's the idea called neutrino fog. So we recommended at least one experiment to be built that would reach the sensitivity so to reach this neutrino fog in underground experiment. And hopefully that gets hosted in the US at the Sanford Underground Research Facility, which is the same underground lab which hosts the DUNE experiments for neutrino physics. And now towards the beginning of the universe, if the fluctuations of the densities in the universe today is really ultimately quantum nature, we expect that is supposed to follow more or less just a Gaussian fluctuation of some sort. And indeed, the data says that it is actually a beautiful Gaussian. And of course, it may deviate from Gaussian in the tail. That might tell us more about the nature of inflation at the end of the day. But at least this is an incredible evidence that this idea seems to pan out with the data. And also data shows that the inflation lasted a certain amount of time so that the same size of density fluctuation persisted over many decades of expansion, as you see in this plot as well. So there's a lot of circumstantial evidence that inflation really was the cause of this quantum fluctuation. So the program we put together then try to address all of these questions in a comprehensive way. So if you take any telescope trying to look at as far as possible, eventually you hit a wall where the universe becomes so dense and hot the light cannot penetrate beyond that wall, and that's where the cosmic microwave background came from. But using the nuclear physics experiments, people understood what was going on. The universe was only 3 minutes old. That's when the protons and neutrons were moving independently from each other. But we can simulate this event in a laboratory to see how they can stick together to form nuclei like helium. And that would tell us that the hydrogen to helium ratio must be about 3 to 1 in their mass. And indeed, if you look at the sky, that's the ratio we observe in the universe today. So that's why we're convinced we at least understand this far back to the beginning of the universe. But the nature of dark matter is supposed to tell us what was going on much earlier on when dark matter was born. Higgs boson went through this phase transition of some kind that flows into the universe today that happened presumably somewhere around here. We'd like to understand the nature of this transition. And the neutrinos may have played this role of reshuffling matter and antimatter much, much earlier on. And inflation is really the beginning of all. And when the universe is being stretched by an enormous amount, the whole space and time starts to wobble, which is nothing but the gravitational wave we've heard a lot about during this meeting. And that gravitational wave would also wobble the photons coming from microwave background, producing a particular kind of polarization, which we hope to detect by mounting experiments both at the South Pole and Chile. And that's our program. That's the way we would like to approach all of these amazing questions about the quantum universe. In addition, there was also a report yesterday from DESI collaboration trying to understand where we're heading to, namely the fate of the universe. And that is actually governed by the nature of another mysterious object called dark energy. They came up with a new insight into the nature of dark energy. We will see how that would pan out. But that would also eventually tell us whether the universe is heading to an end, where it is completely ripped apart at some instance, or it would just keep going on with an accelerated expansion. Or if the result reported by DESI yesterday is right, then the accelerated expansion would probably go back into a decelerated expansion in sometime in the future of the universe. So that's the way we try to get a comprehensive picture about the quantum universe. So, and in addition, we also recommended new initiatives in the particle astrophysics, and the IceCube has been amazing, being able to take a snapshot of the galactic disk using neutrinos, not using light. And also they have seen neutrons coming from the supermassive black holes in other galaxies. And both IceCube and CTA, looking for gamma rays, would help us understand the nature of dark matter, which may be annihilated or decaying in the galactic halo today much better. So that's the way we like to also proceed on these questions. And to be able to come up with a balanced program, we recommended a new funding line, which we dubbed ASTE, Advanced Science and Technology through Agile Experiments, and meant to support small-scale experiments based on innovative ideas, especially for early career scientists, to actually keep the field healthy and vibrant, and looking into a low-hanging fruits of many interesting subjects, including the other possibilities about the nature of dark matter, like axion, lighter WIMPs, wave-like particles, and so on and so forth. So that kind of the new initiative, we hope, would start addressing the nature of dark matter in a much more comprehensive fashion. And we also care a lot about diversity, inclusion, and equity. So we said the inherent curiosity driving our exploration of the natural world is a universal aspect of human nature. The shared curiosity serves as a driving force behind our commitment to strengthening and expanding this workforce, prompting us to actively seek talent from all corners of society, regions of the country, and on a global scale. And we even decided to call discrimination and harassment in a scientific environment as a scientific misconduct. And we try to come up with concrete items the agencies can actually work on. So fortunately, after our report was released, the media coverage has been fairly positive. One article that surprised me is an article written by Adrian Cho for Science, and the headline said, "Particle physicists dream small." I was like, what? We thought we were ambitious? But if you read the article, it's clear what he meant. The particle physicists in the United States have released a long-range plan that looks less like a child's wish list and more like a parent's cautious budget. So I had to show this to my kids to make sure they understand this. And the New York Times picked up on this ambitious idea of the muon shot, and so did Science. It's on the front cover. But the article actually that made me the happiest is the one by Dan Garisto. So he was very critical of a field after the SNOMAS process, thinking that we will never reach a consensus of any sort. But he actually wrote an article, and he even tweeted, and let me read his tweet here. When SNOMAS ended last year, I wondered how particle physicists were ever going to reach consensus that worked within a budget, was still ambitious, and didn't alienate huge swath of the community. Somehow, the P5 report does all this. And only after seeing this tweet, I started to feel, okay, maybe I'm not going to get a pie. So anyway, that's what we recommended. And so, of course, it takes a while for this kind of recommendation to be implemented. So we are looking forward to implementation by DOE and NSF starting in FY 2026. Thank you.
So thank you, Hitoshi, and thank you for all the work of P5, which was absolutely amazing. So as usual, we have time for questions or comments from the audience, or also people who happen to be online. And find your way to a microphone, and when you're ready, you can go ahead.
Yeah, thanks a lot, Hitoshi, for this wonderful presentation. Did you take into account, into your considerations, the plans of the Chinese electron-positron collider, which is probably 1/3 of the price of the FCC, 15 years earlier in operation, and has the same performance?
Yeah, so that's an excellent question, and I understand this is recorded, so hopefully it doesn't reach the Congress. So what we meant in the recommendation is the following. So we recommended to be involved in FCCE in Europe or IOC in Japan, and we said that both of the facilities would meet our scientific requirement. And CEPC that is being discussed in China, of course, has the same level of the scientific sensitivity as the other two projects. So by saying that we endorse the scientific capability of FCCE and IOC, by extension, we're endorsing the scientific capability of CEPC as well. But we are quite concerned by showing active interest and involved in a project in China in the current climate that might backfire in some way. So we hope by not saying anything about the Chinese project at this moment would actually preserve our ability to be able to involved in the project in the future once the situation improves. So that's the sort of, the fine line we had to walk through when we actually crafted this text. I hope that makes sense.
Hi, Hitoshi. Thank you. You have done a great job promoting this vision. Somehow, my questions pretty are already answered by your question. But maybe let me rephrase another way. I mean, given the budget constraint, it's ever important to have international collaboration on this big project. So my question is to you, similar to the last one. How much constraint your current recommendation is given by the geopolitical challenges facing this?
Well, it's clear that there are many impacts of geopolitical challenges. For example, one proposal to have this the new dark matter experiment reaching the neutrino fog would require 60 tons of xenon, and much of the xenon is produced in Ukraine and China, if I understand correctly. So that would affect actually the market prices when you'd like to purchase xenon. Many accelerator experts actually in Russia, and we would love to work with them, but the current situation is making it very difficult. So all of these things, human resources, technical infrastructure, eventually also affect budget. And so we are strongly constrained by the current situation in multiple ways, I'm afraid. And that's a fact. And we didn't say it that way in the report for obvious reasons, but we were very much aware of that situation.
So, Jeff.
Thank you for the presentation and congratulations on a successful P5 process.
Success needs to be seen.
Success in that nobody's pied you so far. Could you comment on the degree to which the particle physics long-range planning is coupled with nuclear physics and astrophysics long-range planning processes? I mean, we're seeing through talks at this conference and kind of the development of the fields in the last few years that these three ostensibly different fields are increasingly strongly coupled. So I'm wondering if you could comment on the degree of cross-pollination?
Yeah, so they're definitely coupled, and certainly the reason why I emphasized why nuclear science are working on neutrinos and what we would like to understand about neutrinos are really complementary, and they help each other to reveal the sort of full picture about neutrinos. So both of them are needed. Otherwise, we wouldn't be able to answer these big questions like whether they save the world, right? So that's very important. And also that we invited Fiona Harrison, who led the Astronomy and Astrophysics Decadal Survey, to our town hall and listened to her. And we read their report and trying to understand their priorities. And CMBS4 and IceCube Gen 2 are actually common priorities for us and also Astronomy and Astrophysics, the Decadal Survey, and so is Rubin. So many of these things are multi-pronged and need support from all different communities. And we would need to make sure that agencies responsible for each field can work together to make these projects happen. Already on this list you see that SCMBS4 is a joint project of DOE High Energy Physics and NSF Astronomy, not physics. That's already a rather unusual combination you see, but that is what it takes to realize the science we aspire to.
Thank you.
Okay, I don't see any more people standing in line, so we should all thank Hitoshi again.
Thank you for your attention.
Okay, and of course, one way in which nuclear and particle physics are intimately connected is in our need to use accelerators. And we need to use accelerators that don't exist yet. And to tell us about opportunities and challenges in accelerator physics, we have Andrei A from J Lab. And we'll listen to him, please, when you're ready.
And the pointer.
Oh, maybe Hitoshi.
Hitoshi. Thank you. Right, good morning, everyone. So I'm really pleasure to be here. So I'm Andrei A. I'm representing Jefferson Lab and Old Dominion University, and also representing a large community of accelerator scientists who are really excited about this projects in accelerator science, which these two long-range plans put together, including Higgs factory, possible multi-TV collider, electron-ion collider. And I would like to discuss all these projects very briefly, trying to find connections between them and describe accelerator science challenges. And while discussing all these projects, I would like to remind and keep a couple thoughts in mind. First of all, that there is a school of thought that scientific revolutions are driven by paradigm change. That's of course correct, but also simultaneously with that, scientific revolutions are more often driven by new tools, the new concepts. That's another school of thoughts. I'd like to keep that in mind. And also I would like to look at that, all projects at the end of the lecture, through a lens of so-called Pasteur quadrant, which was suggested by Donald Stokes, which allows to kind of analyze whatever you do in research through this two-dimensional plot, which plots fundamental knowledge impact and practical life impact in society. Now let's run through all these projects which are mentioned in recommendations. Actually, I would like to start from recommendation number 3, which is actually to participate and contribute to Super KEGB accelerator. And here the challenge is for many of these projects, the core of the projects is in interaction region, where detector is there and particles collide. And one of particular challenge of Super KEGB is that they are colliding beams which are much smaller than in comparison with KEGB. So so-called crabbed waist collisions, much smaller beams. And you see how complicated interaction region is around these collisions. So the present challenges of this collider is to further squeeze the beams, another factor of 3 or so, and increase currents, while dealing with events like sudden beam loss and background of beam halo, which occasionally cause damage of these collimators as seen here. So squeezing beam downs requires all this and a lot of efforts. Possibly interaction region upgrade would be needed, to which of course would be great for us physicists to contribute. Another recommendation, so now we look at high lumen LHC. This is another collider where a lot of challenges are centered around the interaction region. And in this particular case, it's a collision with large crossing angle, with crabbed collisions. So you see here a very simplified picture of how these collisions look like. So you have beams which come into collisions, and then if you don't crab them, they will not overlap completely at the interaction point. So you need to give them a kick so they will overlap and give full luminosity, and then uncrab it with some other kicks. So this is done with these so-called crab cavities. So that was never done in hadron colliders. It was done electron-positron colliders, where there is synchronous radiation which corrects all your mistakes. So here you need to crab the beams and uncrab that and make sure that it's all done accurately, so there is no remnant motion of the beams after. So International Linear Collider, as mentioned, indeed a very mature design developed by global design efforts, have technical design report, would be ready for construction, shovel ready, have key demonstrations like demonstration of final focus system with 44 nanometers beam size achieved, which would be equivalent to ILC requirements at that energy. And also SRF cavities and including cryomodel production yield, all demonstrated. But interesting point is that after ILC developed, been already many years, there many other ideas emerged. So how to make it even better? And one of these ideas is shown here. You can actually create cavities which would look a bit different than ILC cavity. Instead of standing wave cavities, where you have two traveling waves and only one accelerate particles, you can create a traveling wave structure in superconducting sense, where all your voltage will go to acceleration, and you increase gradient almost factor of 2. So that's a novel idea which needs development, but this could improve ILC. Another version of Higgs factory is CLIQ. Of course, CLIQ was originally designed to be 3 TV machine, but you can also build a Higgs energy machine. That's normal conducting cavities needed, and you can build it, principle. But again, so accelerator community is not just sitting waiting when funding is coming and so on, developing new ideas. And in this particular case, a new idea is so-called C-cube. This is C, and this is called cool copper collider. So it happens, according to these measurements shown here, that if you cool copper to liquid nitrogen temperature, it can withstand much higher accelerating gradient. And that's what idea behind this cool copper collider, which could be a much shorter collider, and would also preserve some costs and so on, and could fit to smaller size. So great. So another good bad idea how to build Higgs factories. Another thing. So when linear collider collides bunches, so the energy loss is actually very small during collisions. Okay, beams are disrupted, but energy losses are small. It means that you can take energy back from these beams, which could be megawatt, tens of megawatt beams, take that energy back. So in fact, the very first idea of linear collider shown here assumed energy recovery back to 65. So actually many energy recovery based colliders ideas, Higgs factories, emerged. One of them is shown here, energy recovery linear collider concept, where you have actually two Linux, one for acceleration, another for deceleration. They are connected via RF couplers, so that beams accelerate and then decelerate in another Linux, taking the energy back. So as correspondingly, you may have larger current, you may have high luminosity, much higher luminosity. This collider can also benefit from these double axis superconducting cavities, which have been developed and actually demonstrated in a small scale. Also, if you can make this cavity work at 4 Kelvin instead of 2 Kelvin, with niobium-13 thin film covering these cavities, you can save a lot of cryo power and make this collider actually competitive. And various other ideas of energy recovery-based Higgs factories emerge. I'm not going to go through all of them, just to mention this last one, actually called ghost linear collider. So also energy recovery collider, but you collide simultaneously electron-positrons and electron-positrons to compensate charges of the beams at the IP as well. And also you accelerate both electrons, positrons, so that your LINAC actually don't see any charge. Correspondingly, there are no high order modes excited in the first order in this collider. I call this even not a concept, it's a cartoon. It's not yet well developed. But what it all tells us, the big picture, is the following. There is ILC, which is really TDR, ready for construction, can meet requirements. But there are also various other ideas which I mentioned, including HAF, which is actually a plasma-based asymmetric collider, which I'm discussing later in the talks. What this tells us, this large number of ideas post-ILC, this is effectively a partial survey of a community of accelerator scientists in terms of interest of particular technologies they are interested in development. So if ILC would need to be built indeed, it might need to be refreshed in terms of design to be compatible or maybe based on this technology or at least compatible with some of these novel ideas which are much more promising. But there is FCC-EE, which is a circular collider, Higgs factory, a lot of efforts coming, and this can be ready for construction very soon. So FCC plus or minus collider, 90 kilometers tunnel close to CERN. This is a two-stage project starting from Higgs factories and then proton-proton collider. So CDR already received, released, and technical design feasibility study will be released in 25. We're not going to go through a lot of this R&D. There were talks in the sessions, and there will be more talks next sessions, I think, later on. Just to mention one, you need to make this collider really very energy efficient. One way to do that is to have good accelerating cavities. You show here examples of superconducting cavity, normal conducting cavity, as well as very high efficiency klystrons. Klystrons, very old technology, 100 years or something, maybe less. But anyway, you can make them even more efficient, apparently. So, and there are many novel ideas coming to make these klystrons much better. Of course, interaction region is really heart of many of these challenges in accelerator science projects is interaction region. And not surprisingly, this is true also for FCC. And that's the reason why there is prototypes going on for interaction region of FCC, and mock-up is built in this collaboration as shown here. Of this central region, how it's all integrated, how it's all supported, how cooling is done for central detector, how it interfaces with magnets, prototypes of the magnets, measurements at quality, and so on. So a lot of challenges. So Hadron Collider based on FCC would be a natural next step. So going to 100 TeV center of mass, equivalent roughly to 10 TeV of parton energies. And challenges listed here. One of the most notable challenge include creation of high field magnets, 14 to 20 Tesla magnets, and a number of other challenges as well. So let me now switch to other recommendations, nuclear physics recommendations. So accelerator physics projects in that report. So continuing running our facilities, of course, but also expeditious completion of electron-ion collider. So there will be a special talk, just the next session by Seryi Nagaitsev. So I'm just going to very briefly show 3 slides about electron-ion collider. It will be based on RIG, using existing storage rings of RIG for protons, but increasing currents, increasing number of bunches, and creating 2 new accelerator electron rings. One storage ring for electrons, again with large current, 2.5 amps, and also a rapid cycling synchrotron. Interaction region is, again, a very important challenge and point of efforts for electron-ion collider. We need to have flat beam collisions. In order to create flat beam collisions, we also actually need cooling, which I'll mention in a moment. And also we need to have large crossing angle for collisions. And crab cavities again. This is a picture of crab cavities. So to be included in these collisions. So cooling, why do we need cooling? And why do we need strong hadron cooling? Strong hadron cooling is needed to counteract so-called interbeam scattering, which blows up the beam size, and to create flat beams, small beam size. Why do we call it strong? Because if you take conventional electron cooling or stochastic cooling, you scale it to parameters of EIC, energy, and so on, density, it will be too weak. So we need something much stronger. So we call it strong. And strong, you can realize it in a variety of methods. We at this moment assume that strong hadron cooling is based on so-called coherent electron cooling, when a proton travels together with this electron and leaves a kind of fingerprint in electron beam. So kind of like wakes and so on. So this fingerprint is then propagates and amplifies, and then merge back with proton beam, this fingerprint in electron beam, and acts back on that. So this process of amplification is called coherent electron cooling. So there are a number of challenges which Seryi will describe in his talk, like large current of electron beam, which at this energy would be equivalent to 15 megawatts. So you need to recover that energy. So ERL, energy recovery link, is needed. So then the electrons and protons beams first propagate each other to create this fingerprint, then separate, go for 100 meters, and then join again. So this joining again longitudinally need to be done with precision of a fraction of a micron, maybe 200 nanometers or something like that. That's a challenge. And then also electron beam needs to be extremely quiet, so that on this electron beam you can actually see that fingerprint very precisely. A lot of challenges which our teams are working on. Interaction region is, you see here, you need to collide hadrons and electrons. And this is very complicated integration of a lot of magnets, which you see here includes a variety of superconducting magnets, which include sometimes electron magnet, hadron magnet, as well as a detector inside. So again, so integration, creation of these collisions at 25 milliradian angle, and compensation and compensation of crab kicks. Another recommendation. What's mentioned here in recommendation 4 is a staged upgrade of CBUF. So first of all, operation of CBUF with polarized and unpolarized positron beams, and also energy upgrade to more than 20 GeV. How that's done? What is the concept? So there will be a special talk tomorrow by Alex Bogach, but just briefly. So CBUF is a machine where you use superconducting Linux to go around like 5 times, accelerating 5 times. So, and of course you're accelerating, the energy changes, and you use in these arcs, you use separate magnet beam lines for each of these different energies. So there is a new accelerator technology which can change the approach, change the paradigm. So you can create, add one more additional arc, shown in green here, with FFA technology, fixed field alternative gradient magnets, which are kind of like shown here as a permanent magnet prototype, where special optics is arranged so that particles of different energies go through the same magnetic aperture. And that's possible, and that's what colleagues are working on as a path forward for 22 GeV energy upgrade of CBUF. Positrons would be realized just before that. And how we create positrons for CBUF? We send polarized electron beam to a target, and photons created in this target carries polarization of initial electron beam, and then pairs created, and you separate positrons. And when, depending on where actually you separate, where you take these positrons coming out of this, you can create a 60% polarized positrons beam and so on. So we'll create a positron source somewhere here in this LURF, and then create additional tunnel and inject it in CBUF. That's how it will be done. Going back to P5 recommendations. 10 TeV center of mass, parton center of mass collider. So muon collider. As Hitoshi mentioned, this is a possible way to achieve these high energies. And as mentioned, of course, muons decay. So you need to create muons first. So you need to have large currents of protons, send it to target, collect it all. So high megawatt targets is one of the challenges. Then you need to have a cooling, very rapidly cool these muons to reduce their phase space. I'll show a picture on the next slide. But then you need to very rapidly accelerate them, and also you need then collide them. And here, in terms of collisions, the challenges are high field magnets, also high energy neutrino radiation, background from muon decays, and also interaction region shielding. Just couple more slides on that. So cooling, how do you cool that? So you can cool muons very quickly only with ionization cooling. When you have an absorber and you lose some of the energies of these muons, and then you reaccelerate it immediately in the cavities. And then you do it many times. So you need to condense all this together to have cavities for acceleration, magnets to focus muons, and also to mix all degrees of freedoms and pack that all very densely. You need high field magnets for that, and you need to really put it integrated together so it will be working very well. So that's one of the most important next steps, challenge for muon collider, to demonstrate that it works. So new cooling demonstration facility, which is kind of like outlined here at the bottom, is needed. There was a cooling demonstration, a mice, which was not 6-dimensional, 4-dimensional, and just single particle experiment. This new demonstration facility must be 6-dimensional and not single particle, but also involves just a bunch to show that you can cool a bunch. And interaction region. So since muons are decaying, so you need to take care of these decays and make sure that your detector can still measure physics. So the way it's envisioned to deal with that is to create some special nozzles in interaction region made from tungsten, so that you block all these secondaries and muons coming from upstream's decays, and then collisions measured in interaction region are more or less clean. So you see that these decays happen in the beamlines upstream, detector is more clean. Another thing, of course, in the ring, the muons decay and emit neutrinos. Somehow on the surface you might need to worry about radiation levels. You can kind of smear it down by moving beamlines with movers. That's one of the approach. This is something which, of course, needs to be worked on very in much details. Now, plasma colliders were mentioned. So if you're talking about plasma colliders, you have a variety of methods how you can create plasma acceleration-based colliders. One of them is laser-driven plasma acceleration, shown here. You use laser pulse to create a bubble in plasma, and then you accelerate electrons in that bubble. Or you create that bubble with a drive bunch of electrons. That would be a beam-driven collider shown here. Two different concepts. Some of the challenges are similar. So in terms of experimental demonstration, either beam-driven or electron or laser-driven colliders demonstrated around 10 GeV acceleration with rather good efficiency and so on, but for single stage. So the next challenges for this type of colliders would be laser repetition rate and efficiency for laser-driven collider, beam quality preservation for both of them, and multi-stage development. So just you need to do it in multiple stages, all this acceleration, many stages of laser acceleration and many stages of beam-driven acceleration. And also, so far these concepts are kind of focused and designed to maybe 1.5 TeV energy and so on. This needs to be taken to 10 TeV center of mass designs. So I promised to describe this half idea. I think this is a novel idea, really thinking out of the box. And actually, I have forgot to mention one additional challenge here, the positron accelerations. So you see how this bubble look like. So it's very natural to place electron beam here. But if you place positrons, they will be decelerated. So you need to place positrons behind the bubble, but there is really little phase space here. Of course, easy solution would be to use antimatter and create this bubble from antimatter, but antimatter is not yet available. And of course, then you need to think about how you really create positron accelerations. And this hybrid collider concepts really solves that. So this is plasma acceleration collider, where electrons are accelerated in plasma, in beam-driven plasma acceleration to 500 GeV. But positrons are accelerated in a conventional LINAC, so without any problems with plasma acceleration. And then, in the center of mass, you have boosted collisions, but 250 GeV center of mass. Very good innovative concept, very interesting. So also actively developed. So several key accelerator challenges are shown here. Of course, you need to demonstrate multi-staging, emittance preservation, and so on, and also optimization of your beam, conventional beam collisions. So plasma wave field acceleration aiming at colliders is great. But what's really very interesting is coming and very important, that what starts to come out is applications from these plasma accelerations. So one of them is shown here at the top, and this is free electron lasers started to lace based on laser-driven plasma acceleration and beam-driven plasma accelerations. So there are already several publications, high-level publications. First one in 2021, lasing at 27 nanometers, shown here, very compact FEL. Probably average brightness is still low and so on, but this will come. And also several others are coming. So this demonstration of FEL lasing confirms plasma wave field acceleration beam quality, which will be important for colliders, but also important for various applications. And also I would like to mention another project which is related to plasma acceleration, beam-driven plasma acceleration, which is AWAKE experiment at CERN, where you accelerate electrons not with another accelerator electron beam, but with protons. You use proton beams to excite plasma wave and then accelerate electrons in there. So application from that AWAKE may be the first possible nuclear physics experiment. Low luminosity maybe, but you can imagine colliding 50 GeV electrons accelerated through this plasma with 7 TeV proton beam. Well, possible applications. Anyway, what are all these challenges? So how do we combine and analyze all this, what I just described, together? And I listed here a lot of collider designs, Higgs factories, ILC, click, C3, and so on. And many of these challenges are really common, like interaction region, machine detector interface, applicable to most of them, all of them. So final focus and collimation, beam cooling, which needs to be beyond state of the art, applicable to muon collider, applicable to EIC, and so on. And many of these challenges require a common R&D approach, even for completely different concepts. And let me show you an example of this common approach for seemingly very different concepts. So let's take muon collider design and let's take plasma collider design. So here, what you see here, we'll come to that, but let me describe these pictures a bit slowly. So in all of these colliders, you need to focus the beam, and you need interaction region. So here a picture of plasma-based collider on the right, beam-driven collider in this way. So plasma acceleration have very large accelerating gradient. So it allows you to have very small facility, footprint. But beam delivery is long. So if you take it from ILC design, which is, you see, almost 2.5 kilometers per site, you get 5 kilometers only for beam delivery system. And then you're saying, well, are you using advantages of plasma acceleration, huge acceleration? Well, maybe not. But you can note here that final focus system, the way to focus the beam, is very small fraction of this beam delivery system. And all this thing is actually taken, all this length, most of that, taken by collimation system. So that's one observation. Another observation, so in this multi-TeV plasma collider, you actually may expect to generate a lot of beam halo, beam tails, in these plasma acceleration stages. So collimating them further downstream would be too late. So you create some damage, you need to compensate it locally. So this collimation system actually might need to be distributed between these plasma acceleration cells. That's a different approach. Then now look at muon collider. So muon collider needs these nozzles, these tungsten nozzles, to isolate your detector from this background coming from muons and so on, decaying upstream. So looking at that, so muon collider actually, you need to clean the muon beam as well to mitigate this background coming from upstream. So muon collider may actually need similar approach as plasma collider for distributed beam halo cleaning system as in plasma collider. So on the other hand, plasma collider, which may have very large background coming of beam tails coming from these many cells of plasma acceleration, may need some kind of similar kind of nozzle, tungsten nozzle or something in that detector to be able to shorten beam delivery system and make advantage of this high accelerating gradient, which plasma acceleration offers. This is just one example which shows that seemingly very completely different designs of multi-TV colliders needs to be considered together. And on that note, I would like to come to conclusion and would like to look at all this somehow, and looking at all these Higgs factories, multi-TV colliders, and so on. This is Pasteur quadrant, as I mentioned. So this is the direction of Niels Bohr. So all our colliders are here in these directions. Impact on fundamental science, not immediate impact on practical life. But looking at this technology development, so you can imagine that there will be very immediate, almost immediate applications of all this technology. For example, plasma wave field free electron lasers. They will be already having impact both on fundamental science and on practical life. Superconducting permanent magnets for gantries, or proton therapy gantries, and so on, a lot of practical applications. So high field magnets for compact fusion reactors would be one of the applications. Or maybe energy recovery FELs for semiconductor lithography could be another practical applications. So on that note, I would like to conclude with this quote from Michelangelo, who tells that the greater danger for most of us, lies not in setting our aim too high and falling short, but in setting our aim too low and achieving it. So I hope we will set our aim high and we'll try to achieve it. And I would like to conclude with the following. So accelerator science and technology in all these projects, very exciting projects, offer us exciting challenges we would love to work on. Community efforts will result in new advancements in control of beams, of particles and lights, and creation of new technologies as well. So future scientific facilities, I'm sure, which are based on these accelerators, will push frontiers of science and will also stimulate development of a variety of applications that will benefit society in the nearest future. I would like to acknowledge help from many colleagues, and with that, I'm ready for questions. Thank you.
All right, as usual, if you have questions or comments, please come up to the mics. One quick thing I want to remind people of is that after the Q&A session, APS President Yankee Kim will make a few remarks as well, so don't run away. Yes, Sarah.
So during your talk, you spoke about many very exciting, very innovative ideas for future colliders. And not meaning to insult Michelangelo, but given the size of the world accelerator community, its important commitments to Super KKB, EIC, and CBAF, and the fact that we are actually under the budget, the lowest budget shown by Hitoshi in his talk, if we work on all of these in parallel, when would you realistically expect one of these very exciting, innovative ideas to be something ready to use for physics experiments?
Well, Hitoshi, I think, made a very good job of conveying that the committee, like P5 committee and nuclear physics committee, made really selective recommendations of kind of like focusing on just number of things. Of course, we would need to build just one or two colliders and so on, but ideas which are emerging somehow, which promising ideas, might need, whatever we build, might need to absorb all these ideas which are existing already somehow. So to be modern and so on, you need to not to be static and somehow and build something which you designed like 20 years ago. But okay, if you build that, make sure that you use all these ideas. But also in terms of community size, of course, there is a lot of efforts both in nuclear physics, particle physics, but also in accelerator science community in terms of education of next generation colleagues who are really very excited about many of these directions. And we certainly will work together with all generations on these projects.
So any more questions or comments? I had one sort of curiosity question. So of all of these amazing science fiction looking ideas, Which one are you most excited about?
I was promised myself to remain unbiased as much as possible during this talk. You can come to talk to me later if you'd like.
Okay, so on that note, we should thank Andrei and all the other speakers again.
Thank you.
And it is my pleasure to announce APS President Yang-Ki Kim to say some parting remarks related to this Kavli session.
Thank you very much, Andrei. I think first, let's give another big round of applause to our amazing speakers this morning. So as you heard, there have been amazing, very powerful community efforts. So I'd like to thank Division of Nuclear Physics and Division of Particles and Fields and Division of Physics of Beams. So I have a couple of comments. There were some Q&A sessions. I would like to add a couple of things to what already heard. There's one question about the various divisions working together. In fact, the SNOMES process that Hitoshi mentioned, of course, Division of Particles and Fields led the effort, but DPB, Physics of Beams, and Nuclear Physics, Division of the Nuclear Physics DNP, and also DAP, a Division of Astrophysics. I think we have really have inclusive efforts, so there are a lot of multidisciplinary efforts going on, so I'd like to comment on that. Another one, I mentioned this powerful community efforts, and we recognize that, and we want to make sure that this is properly transmitted to our policy makers. So with the help of APS Public Affairs Office and also the APS Physics Policy Committee, so I have written a letter to Senate and House Committee of Appropriations. So that includes the one sentence. I'll just read one sentence among that. The president of APS, I am writing to re-emphasize the importance of long-term community-driven consensus reports in determining the most effective uses for federal science funding. So we are communicating the effort to the policymakers, as I thought you should know. Another comment about the support of our APS members coming to DC, the congressional days and etc. So there are, you heard already, more APS-wide effort and also subfield, for example, Division of Nuclear Physics and Particle Physics, etc. They have their own the effort doing that. But in terms of the APS-wide congressional visits day, that usually take place end of January, I think you already heard earlier. So this year we had 91 members, APS members, including students. They came and visited 110 offices. So this is an amazing success. And APS has provided all their travel and lodging support. So I wanted to know that. There was some question about high school students and that discussion. They had some comments about that, but I'd like to add that the APS together, partnering with the AAPT, there's American Association of Physics Teachers. We have a number of excellent programs for helping high school teachers. As you know, the dynamic high school teachers and their roles are very, very important. So we have quite many excellent programs, and I thought you should know that. Now, as John mentioned earlier, we are truly grateful for the support of the Kavli Foundation, and thanks them again for their important contributions to advancing the dialogue around new challenges and big questions in physics for the next decade and beyond. I look forward to the many remaining events and sessions this week. We are kind of halfway done, or maybe a little more than halfway. I would like to encourage you all to attend our final plenary session tomorrow morning. which will focus on the scientific impact of major facilities. And thank you for joining us, and have a wonderful rest of the day.